Okay, so we have slowly been implementing these different assumptions. So assumptions 2, 3, and 5 have been used to get the form of the scalar field shown on the page below. What we're going to try to do now is we're going to use assumption 4 and see what it tells us. And in fact, it's going to be able to fix the k dependence of these constants ck and ck star. So let's see how that will happen. So we want to use A4 now. But to make life simple, I'm going to use A4 at x is equal to 0. Okay, we've already, in fact, fixed the x dependence. So if we check that it works at x is equal to 0, we know by translations it'll work at any other x. So at x is equal to 0, we've got u dagger of lambda acting on phi of 0, u of lambda is equal to phi of 0. So let's use our mode expansion and work out explicitly what that is. As before, the u dagger and the u operators are going to be able to move through everything except for alpha and alpha k dagger. So u dagger of lambda, phi of naught, u of lambda, what will this be equal to? Well, it will be equal to, in fact, let me do this slightly differently. Let me start off by simply writing down what phi of naught is. Okay, that seems like a better idea. So phi of naught, I just plug in naught everywhere for x. So we'll get d3k over 2 omega k, 2 pi cubed. Then we've got this constant ck, e to the minus ik dot x. If I plug in x as naught, that's e to the naught, which is just 1. So I'll have alpha k plus, and then I will have ck star and alpha k dagger. Good. And this must be equal to u dagger of lambda, phi of naught, u of lambda. And then, as I was saying, we can pull the u dagger and the u through everything except for alpha k and alpha k dagger, because u dagger and u go through any numbers. So this will give us integral d3k over 2 omega k, 2 pi cubed. We've got ck, that's also just a number. Now we'll have the u dagger of lambda, alpha k, and u of lambda. Plus, we'll have ck complex conjugate u dagger of lambda, alpha k, u of lambda. So to actually use this equation, the thing I have to calculate is u dagger of lambda. Let's say, I lost the dagger. Alpha k dagger, u of lambda. To do that, I just want to remind you of how Lorentz transformations, this unitary operator u of lambda, of how they will act. So u of lambda, this is how you perform a Lorentz transformation on the Fock space. Well, if you've got a bunch of particles with momentum k1 up to kn, and you do a Lorentz transformation, each momentum will be transformed. So that's how the Lorentz transformations will act. Next, we know that u dagger of lambda, u of lambda is equal to 1. This is not a property of Lorentz transformations. This is true for any unitary operator. Okay, so this is not special to Lorentz transformations. But what that means is, if we take u dagger of lambda, and we now act on lambda k1 up to lambda kn, well, this is u dagger u on the state k1 up to kn, so we must just get k1 up to kn. So make sure you understand why I wrote that equation. It follows from what we've written down. And equivalently, we can also write u dagger of lambda will be u of lambda inverse. Good. Okay, now let's calculate the operator that we want. And we're going to use the same logic that we just used when studying translations. So we're going to take this operator and we're going to act on a complete basis. And our complete basis is going to be, let's say it's P1 up to Pn, okay? And the basis is given by letting n be arbitrary. So we'll consider 1 particle, 2 particle, 20 particle, 40 particle states. And the momenta and energies of those particles can be anything. Okay, so in the first step, u of lambda simply performs the Lorentz transformation. So we get lambda P1, and every four momenta is transformed. Then alpha k dagger adds a particle to the state, and the particle that is added has a momentum k. And then when we act with u dagger of lambda, this is the same as acting with lambda minus 1. So we remove the lambda from P1, from P2, and so on, all the way up to Pn. But we have a lambda to the minus 1 acting on k. And then finally, I can write this as alpha dagger lambda inverse k on P1 up to Pn. And now what I compare is this first line underlined in blue to this last line underlined in blue. And what you will notice is I have this operator. Look at the first line. I have an operator which doesn't depend on P1 to Pn. Acting on an arbitrary state in the basis is equal to an operator acting on P1 to Pn, and it also doesn't depend on P1 to Pn. So acting on a complete basis, I know that u dagger of lambda, alpha k dagger u of lambda, is equal to alpha dagger lambda inverse k. And because this is true acting on a complete basis, it is true as an operator identity. Good. I can take the dagger of this equation. So if I dagger it, I reverse the order of the operators. So the u of lambda goes to the first position. And when I dagger it, it becomes u dagger of lambda. Alpha k dagger stays in the middle, but when I dagger it, it becomes alpha k. And u dagger of lambda goes to the back. And when I dagger it, it just becomes u of lambda. Then when I dagger alpha dagger, it becomes alpha. So now I know how both alpha and alpha dagger transform. Great. Okay. So now let's come here. And this is the equation that I would like to rewrite. So let me pull it out. This is the equation we're trying to solve at the moment. Good. Here we go. Good. So here it is. And I don't need this thing distracting me in the middle. So these two are equal. Let's now write this again using what we've just learned. Okay. So we've got an integral d3k over 2 omega k 2 pi cubed into ck alpha k plus ck star alpha k dagger. Good, so that's fine. And now, what will this be equal to? Well, we have an integral d3k over 2 omega k 2 pi cubed. And then we've got ck, and then we know that u dagger lambda alpha k u of lambda is alpha of lambda to the minus 1k plus ck star, and now we've got alpha dagger lambda to the minus 1 of k. So this is the equation that we've got. Good. Now, I'm going to make a change of variables on both sides of the equation. So For the blue term, I'm going to say change from K mu to P mu. So remember, the K naught and the P naught components are not variables of integration, but I can change the spatial momentum K integration variable into a spatial momentum P integration variable. And for the green term, I'm going to change from lambda minus 1K to a new integration variable, which is P, okay? So actually, on the left-hand side of the equation, I'm just relabeling. I'm saying let K be equal to P, okay? So that's just a relabeling. Okay, let's rewrite the green term. So first of all, this is a Lorentz transformation, and we know that the measure is Lorentz invariant. So we can write the integral d3p over 2 omega p 2 pi cubed. That's because the measure is Lorentz invariant. Then ck will become c of lambda p, because k is lambda on p. And then we've got alpha p plus c lambda p star, again because k is lambda p, and we've got alpha dagger on p. And this will be equal to, now for the blue term, we have simply renamed our integration variable to p. So we've got an integral d3p over 2 omega p 2 pi cubed. And we've got cp alpha p plus cp star alpha p dagger. Good. And this is the equation that we need to satisfy axiom 4. We'll continue in a moment.